All right, so 4.3, the fundamental theorem of calculus. And if you notice, you cannot even say the word fundamental without saying the word fun, right? So the fun theorem of calculus, that's one way to abbreviate it. But the fun theorem of calculus is still kind of a mouthful. So I tend to abbreviate it the FTOC. The FTOC. The fun TOC, right? Not the unfun TOC.
Teachers and students,
that's us. That's us.
There are still plenty of spots available to get blood this afternoon.
Okay.
Students, please go to the library between classes to sign up for a time slot and get a pass. Also, just a reminder, anyone that is interested in trying out for baseball this year, there is a mandatory meeting this afternoon at 4:30 in the commons area.
At this time, if you could please turn your TVs to channel 4 for the morning announcements. You can also view them online at vhstv.com.
There you go. This is Isaac Barrow, and he was Isaac Newton's teacher at Cambridge University, okay? So how would you like to have Isaac in your class, right? Every mistake you make, Isaac standing up, saying, nope, no, you're wrong there. And so sit down in quiet tea. I don't know. Anyway, what did Isaac Barrow do? Isaac Barrow came up with, or kind of proved, he kind of worked with Newton. But he proved, or the first to come up with this idea of the fundamental theorem of calculus. So every branch of mathematics has its own fundamental theorem. The fundamental theorem of algebra, you didn't learn in Algebra 1 necessarily. The fundamental theorem of algebra basically says that a polynomial of degree n has n complex roots. And that was Gauss. The fundamental theorem of calculus says something as well, and we're going to learn that today. But the idea behind the fundamental theorem of calculus is essentially that the derivative process and the integration process are related to each other very much like division is related to multiplication, which is how? They're inverse operations of each other, okay? And so Isaac Barrow was the first kind of to prove that, and because of that, they named the lunar crater on the moon. The Barrow crater on the moon, if you've ever vacationed there, it's kind of a big one. It was named after Isaac Barrow, okay? Isaac Barrow. Nothing on Earth that I know of is named after him. The wheelbarrow is not named after him. So, I don't know if that's an honor. You know, it's like, nothing on Earth is important enough, but something on the moon will name after you. But at least he has that. All right, let's look at the derivative process. In Leibniz notation, I look at that as the derivative process. And in, I don't want to do that. That's the F hole. If I write the integration process, I write it like that. So if you notice, the derivative is actually a process of division. Right? It's the instantaneous rate of change of the y values to the x values. It's a ratio of y to x, but it's a division process. dy essentially divided by dx. The integral is essentially the sum of something times something, right? And this is multiplication. And of course, we've seen that in the finite process that we're coming off of, right? We have our heights times our width. Those are areas of rectangles. So just like division and multiplication are inverses of each other, that is, they undo each other's work, so does the derivative and the integral. The derivative and the integral are inverse operations of each other. And that, essentially, in general, is the fundamental theorem of calculus. Now, there's two different parts of it that we're going to explore separately. Okay, so before we do that, let's quickly review some of our rules of integration. Because once we learn the fundamental theorem of calculus, which is essentially going to be one part, the shortcut rule for integration, it's going to rely heavily on finding antiderivatives. So if we have a constant multiple, we pull it out front, it goes for a ride. If we're integrating a constant k, it just becomes k times x, of course, plus c. This is the power rule. This is like the only general rule of integration that we're going to have that applies to multiple functions that fit a certain pattern. It's the only one. Add 1, divide by the new exponent. Of course, that works when n isn't negative 1. The antiderivative of e is itself. The antiderivative of sine is negative cosine. Secant squared is tangent of x. Secant tangent is secant of x. Of course, this becomes inverse tangent. You already know all these. If you're integrating multiple terms, you can give them each their own integral. I'll review. When the power rule fails, who comes to the rescue? natural log, absolute value of x. Here's a good one. If you're integrating an exponential function that's not base e, it's going to be itself like base e, but you're going to have a correction of 1 over the natural log of the base. For instance, if I have the integral of 3 to the x, you could always do, remember, a guess, check, revise. Because it's exponential, you might think it's 3 to the x plus c. But because the derivative and the integral are inverses of each other, you can check by undoing your integration by differentiating. What would the derivative be? Well, let's see. The derivative of 3 to the x is 3 to the x itself times the natural log of 3, and then c goes to 0. You can compare that to this and say, ooh, I have some heartburn now of a natural log of 3. So I need to now take some antacids, which is going to be the reciprocal of the natural log of 3. So in general, you could say that it's going to be itself and then divided by the natural log of the base. We call this the correction, or I call it the correction. And you're going to get so good at correcting things, you're going to correct it before it happens. Just like you only have to have heartburn 3 times in a row maybe when you're eating the same dish to realize next time you take antacid before you eat it. Because we're learning animals. All right, the antiderivative of cosine is sine. The antiderivative of cosecant squared is negative cotangent. Remember, this negative here is essentially another type of scalar multiple correction. We're going to be off by a negative. Cosecant cotangent, blah, blah, blah. You have all those down. Okay. Here's the FTOC part 1. We have 5 minutes left. The FTOC part 1. Now, some textbooks call this part 2. I call it part 1. It doesn't matter if you call it part 1 or part 2. What's important is that you understand what the theorem says. Okay? So here's what this one says. If f is continuous on a closed interval, boy, we've seen that before. Apparently, continuity is a really big precondition for a lot of things happening. And we say big F of x is an antiderivative of some function little f. We've seen that notation already. Then here we go. The definite integral from a to b of little f of x dx is equal to the antiderivative, or an antiderivative big F of x, evaluated from a to b, which then can be evaluated by the following. It becomes big F of b, that means plug in the top, minus big F of a, plug in the bottom. So it's the upper bound minus the lower bound evaluated at inside the antiderivative. This essentially, for all practical purposes, becomes your shortcut rule for definite integration. Okay? Your shortcut rule for definite integration. Let's try it. By the way, one thing here to note, or maybe 2 things. Remember, this doesn't always give us the area. It gives us the net change or the net accumulation. And it's heavily dependent on finding the antiderivative. So we're going to spend a lot of time in this section, especially the next, finding antiderivative. Okay, so using the properties of integrals, I have 2 terms. You don't necessarily need to rewrite it like this and give each of them their own integral. That's kind of unnecessary. We didn't do that with the derivative. We just went boom, boom, boom down the line, term by term. So that's what we're going to do here, okay? What's the antiderivative of e to the x? E to the x, good. Minus, what's the antiderivative of 3 with respect to x? 3x. Do we need the plus c? No, we've seen that. But since this is the first time we're really technically learning it, let's put plus c. There is an antiderivative. It's the general antiderivative. Now, what do we do with it? We evaluate it from 1 to 3. So this is an intermediate step that I want to see. Do not skip this intermediate step. Now, the fundamental theorem says we evaluate it by plugging in the top. So always get in the habit of putting parentheses here. Plug in the top, close parentheses, minus open parentheses, plug in the bottom. E to the first minus 3 plus c. Plug in the top in parentheses, minus plug in the bottom. Now, it's a little bit more critical in the second term because you have a minus sign. If you simplify that, you get e cubed minus 9 plus c minus e plus 3 minus c. What's always going to happen with your plus c's? They will cancel. And therefore, for a definite integral, you do not need to write them. And so the last thing you're going to do here is combine like terms. e cubed minus e, and then you have minus 6. And that is an exact answer that represents the net accumulation of this graph on that interval. Okay? There you go. There's a taste of now officially using the shortcut rule for integration, which means we don't have to like approximate this anymore using numeric methods, Riemann sums or trapezoids. Pretty nice. All right, we'll see you tomorrow. Tomorrow we'll kind of get a little bit more to here, and we'll talk about Friday's test.